Okay, good morning. I'm going to talk about HL5, morphology of HL5 galaxies today. This is work with a few collaborators, Celine and Jayan and Juhan and Sungwook and so on, and they can, okay, Jayan is here, and Juhan is here, and Celine is here, and Sungwook is missing right now. So, ever since I was a boy, I was fascinated by the diversity and the beauty of galaxies. I guess you were the same. Then I waited for more than 40 years for the explanation, but my fellow astronomers didn't come up with clear explanations. So I decided to work on it myself. I was actually motivated by this work with Ho-sung. We made the visual classification of galaxies in GUS survey and studied the fraction of early type galaxies as a function of redshift, and found that the fraction of early type galaxies in high density regions and in low density regions converges at redshift 1 at about 15%. And the natural question to ask is whether or not the galaxies at redshift higher than 1 were completely late type galaxies, and maybe the galaxies have late type morphology when they form. But of course, the data is not deep enough, so we stopped here. And there are many observational and theoretical the studies on the galaxy morphology at high redshift, but there has been no consensus, both from observation and simulation yet. So I used HL5 simulations to study this morphology of galaxies at high redshift. HL5 has ran a flat lambda CDM model using hybrid MPI and OpenMP Ramses code. The simulation box size is a gigaparsec, and the simulation resolution is 1 proper kiloparsec. And we have a zoomed-in region with higher resolution down to 1 kiloparsec, which looks like this: is 1 gigaparsec by 119 and 127 megaparsec. Okay, so there are a few outputs. We have 170 snapshots of the whole simulation data, including dark matter particles and stars and black holes and gas and gravitational potential. And we have also passive Lycon data and some high time resolution data for 5 pre-selected galaxy clusters. These two plots shows dark matter distribution and stars and gas distribution. Then we identified galaxies and made a morphological classification based on stellar mass density distribution. We calculate asymmetry parameter and Searching index. When asymmetry parameter is less than 0.4, we call them symmetric galaxies. And if it's greater than 0.4, they are asymmetric and classified as irregular. For symmetric galaxies, we measure the radial stellar mass density profile and fit Searching profile to the data. And if fit is successful, they are called regular galaxies. If the fit fails, then they are added to irregular type. And the irregular galaxies are divided into disk type and spheroid type depending on the Searching index. And 1.5 is just rule of thumb criteria for us. And here are some examples showing 3 morphological types at redshift 6. And these are disk and spheroid and some merging galaxies classified as irregular. Okay, So let's look at the morphology of galaxies at high redshift. I divide the epochs in this way. The period between z equal 10 and 4, I call it cosmic morning, and 4 and 1.5 noon, and after 1.5 is cosmic afternoon. And to our surprise, the fraction of these galaxies was about 2/3 at all mass at high redshift. So this fraction at z equal 5, 6, 7 is at the level of between 60 and 70%. And irregulars and spheroids were about 15%, and together they were about 30%. So why is this so? So we suspected probably the initial condition guaranteed the formation of disk galaxies. So we calculated the angular momentum due to tidal torque on protogalactic regions set up by the initial condition, which is proportional to the moment of inertial tensor times shear tensor. And in this plot, we looked at the correlation between this initial angular momentum with the actual angular momentum of galaxies at some specific redshift. So we looked at redshift 6 and calculated the angular momentum vector of the total mass and angular momentum vector of the stellar mass, and found there is very tight, strong correlation between the initial angular momentum and the angular momentum of the total mass, which is dominated by dark matter. Okay? The correlation with the stellar component was weaker, but still there's quite a good correlation. So therefore, the internal kinematics of galaxies is governed by the tidal torque set up by the initial conditions, and this is probably responsible for the initial disk morphology, and also the resilience of disk morphology when disk galaxies perturbed or destroyed by strong interactions or mergers. So they temporarily get some different morphology, and then they reacquire disk morphology later, because there is a continuous mass inflow following these initial conditions. Okay, so this visually shows that. On the left, we have the velocity flow of gas component, and on the right, we have velocity flow of the dark matter component. So outside galaxies, so there's this G4, and the formation shows formation of galaxies at G4 and 8 from 8 to 4. And outside galaxies, you can see the velocity pattern is almost identical between gas component and dark matter component. So the mass just follows according to this velocity pattern set up by the initial conditions stored in dark matter component. So, and this was possible because the physical size of Horizon 5 simulation was 1 gigaparsec, and therefore the large-scale velocity field is correctly simulated, and this disk formation, the dominance disk formation, is partly due to our large box size. Okay, so let's look at what happens to spheroidal and irregular morphological types. Here I'm showing the evolution of Selchuk index for 4 galaxies, 4 randomly selected galaxies, down to G equal 4. And you can see this is 1.5. So when Selchuk index is below this line, we call them disk type. Okay? So you can see that in most times, galaxies spend their life as disk, and occasionally they cross and go up, and then as some time later they come down. So they temporarily become irregular. So this is the dotted line is the period when these galaxies were irregular, and and when the Sashik index was not able to calculate it. So they temporarily become either irregular or spheroidal, but they eventually come back to disk type. Okay? And same is true here. So the conclusion is the irregular morphology and spheroidal morphology are incidental and transient. Well, this is all high redshift. There was great news from JWST just a few months ago, proving our results. So there was a preprint we received 2 months ago by Ferreira. They say that we discovered the surprising result. It's not surprising at all, but we already predicted. At redshift greater than 1.5, disk galaxies dominate the overall fraction of morphologies, which was a factor of 10 times more than the seen by HST. Okay, so and they actually made the eyeball classification of this morphology of these galaxies, but they also calculated the Sashik index too. So this is our criteria. So you can see the most galaxies have Sashik indices less than 1.5, and in fact, Dr. Jong-an Lee is calculating these Sashik indices of JWST galaxies again, and he's finding almost 80% of galaxies have disk morphology at redshift higher than 1.5, and he's increasing number of galaxies now. So this is great success of our prediction. Okay, so let's look at the morphology of galaxies at later epoch. So on the left, the plot shows the disk fraction as a function of stellar mass at different redshifts. And you can see that at a given mass, disk fraction ever increases. It monotonically increases. So there's more and more disk types. But as you go to high mass, disk fraction decreases, and therefore spheroid plus irregular type increases. So this was quite surprising, but this is at given mass. So if you follow a specific target galaxy, which is increasing its mass in time, then you actually travel this way. So when you are looking at fixed galaxy, it's getting heavier and becomes more either spheroidal or irregular, of course. So there is some two effect coming in. And we think this is probably because the decrease of merger rate. So in this plot, the y-axis is the fraction of galaxies that have ever experienced major merger during the past 1 giga-year. And you can see at high redshift, almost all galaxies experience merger, okay, above maybe 10 to the 10 solar mass during the past 1 giga-year. But at redshift 0.6, that drops by almost order of magnitude. The drop is larger for smaller mass galaxies and less for more massive galaxies. That's why, so here by this time, accretion completely dominates the mass increase, but at high mass, still merger is quite important in increasing mass, and that makes the difference, the trend for the stellar mass dependence. Okay, so there is also observational study shown in this plot. So here, so we are looking, each point are the galaxies in Abel clusters. We are looking at the cluster-centric radius versus the distance to nearest neighbor of these cluster galaxies. Well, inside one is cluster galaxies, and outside this is the cluster info region. So outside one video radius, you can see these contours are horizontal. So the contours tells you the fraction of early type galaxies, and what the contours tell you is that the galaxy morphology outside clusters is completely, totally dependent on nearest neighbor distance, and is independent of local density. So there is no local density morphology relation. So people, I think everybody is still educated that there is morphology density relation. There's no morphology density relation because there's a lot of density increase between 10 times the virial radius and 1 times the virial radius, and you can see there's no dependence. The dependence, there's apparent dependence because statistically, as we approach to clusters, the nearest neighbor distance decreases. And it's actually nearest neighbor which is affecting the morphology. But inside the virial radius, the contours are all vertical, regardless of morphological type of neighbor. Okay? When the neighbor is spiral or early type galaxies, the contours are vertical, which means as you approach the center of cluster, there is more and more early type galaxies. So we found this morphology cluster-centric radius relation is emerging in our simulation. So let's look at this panel. So sorry about the size of the plot, but you can, it's okay to look at, it's enough. So each line shows the position of galaxies in stellar mass versus the cluster-centric radius at redshift 1 and 0.6. So each line is one galaxy. Okay? So it's just connected. The yellow is the position at redshift 1, and this violet is the position at z equal 0.6. Okay. So you can see, and in this column are the galaxies which ends up being inside the core of galaxy cluster at z equal 0.6, less than 0.1 virial radius. And these are the galaxies which arrive at the outskirts of clusters. So when we looked at these galaxies arrived at the center of cluster, there are less massive galaxies and massive galaxies at the core. And we see that all these the small mass galaxies are the galaxies merged recently. Okay? So D was larger than one. So they were outside the virial radius at z equal 1, but at z equal 0.6, they're at the center. Okay? But they are all small mass galaxies. And the massive galaxies were always within about 0.1. So between z equal 1 and 0.6, they were just orbiting around inside the core. And they maintain this heavy mass. And then these galaxies, so when you look at this cluster-centric radius versus searching index and asymmetry, you see these massive galaxies have large asymmetry and also large searching index. And these light ones are these ones. So they were at the D larger than 1 and then came in, and they have small asymmetry and small searching index. So they're still disk galaxies. But these heavy galaxies were orbiting around and pass through the center of cluster, and they get stripped and has large asymmetry and also spherical shape. And don't have much time, but the galaxies outside, they were the most galaxies at large cluster-centric radius are either recently merged galaxies or the small galaxies orbiting without changing asymmetry and search index. So we actually see the development of the morphology cluster-centric radius in clusters. So at the center, there's many galaxies with searching index larger than 1.5, but at the outskirts, it's fewer. And I didn't have time to explain this one, but basically at high redshift, the searching index of galaxies which arrived at the center, they had on average searching index corresponding to disk galaxies, and they were the same as the galaxies at outside. But at G equal 0.6, they on average they have very large searching index compared to these ones. So and this bifurcation occurs at around after G equal 2. So G equal 2 or 1.5 is the time when this morphology cluster-centric radius start to emerge. Okay, so that's all. So let me summarize. We made HL5 cosmological hydrodynamic simulations and used HL5 galaxies to study morphology. I think we did this disk domination. We found this disk domination because of this, thanks to the size of the simulation. In this plot, I'm showing the velocity correlation function as a function of separation when we vary the box size. This is just the analytical calculation. So in the case of HL4, which has 4,500 megaparsec, this is the velocity correlation function. So you can consider it is almost correct. But if you have a simulation box size of 100 megaparsec, then your velocity correlation function is completely wrong. So we studied the galaxies at high redshift, and we found 2/3 of galaxies are disk galaxies. And there is an amazing agreement with recent JWST observation. And we think this disk morphology is driven and maintained by the tidal torque imprinted in initial conditions. And whereas spheroidal and irregular galaxies at this epoch are incidental and transient, but as they become more massive, there is a definite trend toward spheroidal and irregular galaxies. To our surprise, disk morphology monotonically increases in time at all masses, and this spheroidal and irregular morphology fraction is higher for higher mass. Okay, so let me close here. Thank you.
Thank you for that very nice talk. Are there any questions? I think Ho-sung was first, I think. Sorry.
Could you go back to the slide where you show the disk fraction as a function of redshift and as a function of stellar mass? Disk fraction. This one, yeah. I might have misunderstood. So, could you explain again why the disk fraction decreases and increases with redshift for a given mass?
For a given mass.
Yeah.
So, for example, at this epoch, let's compare these two epochs. So the galaxies which belong to this mass bin move to the other bin in the later epoch, and here the galaxies belonging to this bin were actually in this bin before. So they are moving to the right as they increase their mass. At the same time, the merger rate is decreasing monotonically. So the merger and strong interaction, close encounter, is the way for galaxies to acquire either irregular or spheroidal galaxies. But this rate is monotonically decreasing. So these newly born galaxies, they experience less amount of mergers. So I think that's the reason.
Okay, when you classify galaxies, do you project the galaxies into two-dimensional plane and fit the searching index and the classified galaxies, or is it three-dimensional classification?
Yes, the searching index is defined in the projected distribution. So we also calculated the INS2 profile, which is in 3D, but in the case of searching index, we rotate the galaxies so that we can make a face-on image and then project it and then make such a fit.
Thank you.
David, can you wait for the microphone is coming?
Thank you. Can you give predictions on the distribution of effective radius? Because if the static index is below 1 and the effective radius is, say, above 1 kiloparsec, then that will correspond to ultra-diffuse galaxies.
Well, this one is 0.7.
Yeah, but the effective radius?
Effective radius?
Yes. How does it evolve with redshift?
I didn't calculate it, but that's in co-moving coordinate is something like 15 or 25 megaparsec, and it's probably about 2 or 3 proper kiloparsec effective radius. But we go out to a few effective radius when we make the fit. So we go 90% of mass, stellar mass, as the fitting range. Well, the simulation resolution is not high, so this is almost we marginally able to do it. Okay. So.
Are there any other questions? So I have a question myself.
Yep.
So if spheroidal or irregular type are transients, that is, it's a transient morphology,
Right.
which is generated by, if I understand you correctly, it was generated by interactions or mergers.
Mm-hmm.
Can I ask about star formation? So there are, I know this is beyond what you've been doing, but there are starburst galaxies which experience this very intense period of star formation.
Right.
Does that mean that all starburst galaxies are irregular type or spheroidal type?
So part of the reason that our result doesn't agree with some of the observational report is because observation is very much affected by this the visual appearance of these galaxies, which depends on starburst. Okay? So some of the starburst galaxies may be classified as regular galaxies and disk, but in observationally they look very patchy, so they probably classify the irregular galaxy. So the fraction of irregular galaxies may differ between us and observers.
Okay.
So, yeah.
Thank you. If there are no other questions, we should thank Chamon again. Thank you.
Thank you. Thank you.